Hey everyone, and welcome back for another deep dive. If you're new here, don't forget to hit that like button, subscribe, and click the notification bell so you don't miss any future episodes.
You got it.
Today we're going to be talking about climatology and atmospheric science.
Yes.
It's really fascinating stuff, whether you're a UPSC aspirant, a senior school student prepping for exams, or just someone who likes to know what's going on in the world.
Absolutely.
So to guide us through all this, we have our expert here.
Thanks for having me.
And first things first, I think we need to clear up a common confusion. What exactly is the difference between weather and climate? We hear these terms all the time, but they're often used interchangeably, and that's not quite right, is it?
Yeah, no, that's right. They are distinct but connected concepts. So weather is what's happening in the atmosphere right now. Is it sunny? Is it rainy? Is it windy? That's weather. Climate, on the other hand, is the long-term average of weather patterns over a significant period of time, usually 30 years or more.
Okay, so think of it this way. Weather is your mood, which can change from minute to minute, but climate is more like your personality, which is more stable over time.
That's a great analogy.
Now, to really understand our atmosphere, I think it helps to take a trip back in time billions of years ago to see how it actually evolved.
Yeah.
I mean, the air we breathe today, it's vastly different from what enveloped the early Earth.
Oh, absolutely. So picture the early Earth's atmosphere. It's primarily composed of hydrogen and helium, very light gases easily swept away by solar winds, and then volcanic eruptions start releasing gases from the Earth's interior, creating what we call a secondary atmosphere.
So volcanoes kind of shape the air we breathe.
Exactly. These eruptions release nitrogen, carbon dioxide, water vapor, and other gases, creating a much thicker atmosphere. But here's a surprising fact. Oxygen, which is vital for us today, was virtually absent in this early atmosphere.
No oxygen. So how did we get the oxygen?
Life itself played a crucial role. Early bacteria, specifically cyanobacteria, evolved the ability to photosynthesize. They use sunlight, water, and carbon dioxide to create energy, and as a byproduct, released oxygen.
Wow, so these tiny little bacteria transformed our atmosphere into what we have today.
They're the unsung heroes of our planet.
Okay, so fast forward to present day. What's the air we're breathing right now actually made of?
Okay, well, the main components are nitrogen making up about 78%, and then oxygen, which is about 21%.
Right.
And then we have trace amounts of gases like argon, carbon dioxide, and others.
Yeah, and even though they're small in percentage, those trace gases, they have a huge impact on influencing our climate.
They do.
Like carbon dioxide, right?
Exactly. And don't forget about water vapor and those dust particles. They may seem insignificant, but they have significant effects on weather phenomena.
Dust. How do dust particles affect the weather?
Think about it this way. Dust particles act as condensation nuclei. They provide surfaces for water vapor to condense, leading to cloud formation and eventually precipitation. So basically, they're like tiny platforms in the sky where water droplets gather to create those fluffy clouds we see.
Oh, that's pretty cool. Okay, and then there's this term we hear all the time, greenhouse effect. I know it gets thrown around a lot with climate change, but it's actually a natural process that's essential for life, right?
It is. The greenhouse effect, you can think of it like Earth's own thermal blanket. Certain gases in the atmosphere called greenhouse gases, they trap heat from the sun and prevent it from escaping back into space.
So without the greenhouse effect, we'd be living on like a giant ice cube.
Exactly. The average temperature of Earth would be about negative 18 degrees Celsius. Much too cold for life as we know it.
Brr. So what are the key greenhouse gases that keep us warm?
The main ones are water vapor, carbon dioxide, methane, ozone, and fluorinated gases. Now, it's important to note that not all greenhouse gases are created equal. Their impact depends on their concentration in the atmosphere, their lifespan, and how effectively they trap heat.
It's complicated.
It is a bit of a complex equation.
Okay, so we've talked about the composition of the atmosphere, but what about its structure? I mean, it's not just one big mass of air, right? It's organized into these different layers.
Yeah, it's kind of like a giant invisible layer cake.
Starting from the ground up, we have the troposphere, stratosphere.
You got it. And then mesosphere, thermosphere, and finally the exosphere, which gradually merges with space.
Whoa, that's a lot of layers. So let's break it down a little bit. What happens in each of these layers? Starting with the troposphere where we live.
The troposphere is the densest layer containing most of the atmospheric mass. As you go higher in the troposphere, the temperature decreases. And this is where most of the weather happens, all the clouds and storms and precipitation.
And at the very top of the troposphere, there's a boundary, right?
Yeah, that's the tropopause. It's a zone where the temperature stabilizes before it starts increasing again in the next layer up the stratosphere. And that temperature inversion is largely due to the ozone layer, which is found in the stratosphere. And the ozone layer, it absorbs most of the sun's harmful UV radiation.
It's like Earth's sunscreen.
Pretty much. And above the stratosphere is the mesosphere, where temperatures decrease with altitude again. And this is where most meteors burn up when they enter the Earth's atmosphere.
Oh, wow. It's like a cosmic shooting range.
Yeah.
And I've heard that sometimes you can see those really cool noctilucent clouds in the mesosphere.
Those are a beautiful phenomenon that occur at high latitudes. Then we move up to the thermosphere.
And that's where the International Space Station orbits, right?
It is. The thermosphere is interesting because the temperatures actually increase with altitude due to the absorption of solar radiation. And this layer contains the ionosphere, which is a layer of electrically charged particles. It's crucial for radio communications. And you also see the auroras in the thermosphere.
The northern and southern lights.
Yeah.
Pretty cool.
Oh, spectacular. And finally, we reach the exosphere. It's the outermost layer, and it gradually fades into the vacuum of space.
Okay, so we have this layered atmosphere. Each layer has its own unique features and functions. But I'm curious, how does energy flow within this system? I mean, we're constantly receiving energy from the sun.
Yeah, that's a great question. And that brings us to the concepts of insolation and terrestrial radiation. They are key to understanding Earth's energy balance.
Okay, so insolation first.
Insolation is the incoming solar radiation that reaches the Earth, and it's primarily shortwave radiation, which carries a lot of energy.
It's like a constant energy bath from the sun.
It is. And then the Earth, in turn, radiates energy back into space as longwave radiation, also known as terrestrial radiation. This outgoing energy prevents our planet from overheating.
So it's all about maintaining that balance, right?
Right.
Between the incoming and the outgoing energy.
That's exactly right. That balance is what keeps Earth habitable. If we absorb more energy than we radiate, the planet warms up. If we radiate more than we absorb, it cools down.
And this balance is influenced by things like the composition of the atmosphere,
Yeah,
right?
exactly, especially the concentration of greenhouse gases, because they trap some of that outgoing heat.
Right. Okay, so speaking of solar radiation, have you ever wondered why the sky is blue?
It's a question we get a lot.
What makes it blue?
It's all about scattering of light. When sunlight enters the atmosphere, it gets scattered in all directions by tiny gas molecules and those dust particles we were talking about earlier. Blue light, because it has a shorter wavelength, is scattered more effectively than other colors. And that makes the sky appear blue to our eyes.
It's not that the sky itself is blue, it's the way the light is scattered.
You got it. And then at sunrise and sunset, when sunlight has to travel through a thicker layer of atmosphere, we see those vibrant reds and oranges because the blue light has been scattered away.
That's pretty cool. So now that we've covered some of the basics of the atmosphere, let's move on to temperature distribution.
Sounds good. So we're talking temperature distribution, but before we jump into that, maybe we should take a quick detour and talk about clouds.
Oh yeah, those fluffy things up in the sky, they're pretty important,
But
right?
definitely more than meets the eye when it comes to clouds.
Yeah.
They form through this process called condensation. So warm, moist air rises, it cools, and eventually reaches a point where it can't hold all of its water vapor.
Okay.
And some of that vapor condenses into these tiny water droplets or even ice crystals, and that's what forms the clouds we see.
Right, so the dust particles we talked about earlier act like these little seeds for the clouds to grow around.
Exactly. They're called condensation nuclei. And the type of cloud that forms depends on a few things, like the altitude, the temperature, how much moisture is in the air. You have those wispy cirrus clouds way up high.
Yeah, those look like someone took a paintbrush to the sky.
Those are made mostly of ice crystals. Then there are those fluffy cumulus clouds we see on sunny days.
Like cotton balls.
Yeah, those are typically found at mid-altitudes. They got a flat base and a dome-shaped top. Now they can develop into those powerful thunderclouds, which are called cumulonimbus clouds.
Oh yeah, those are the dramatic ones.
Yeah.
And then what about those like gray sheet-like clouds that seem to cover the entire sky?
Those are stratus clouds, typically found at lower altitudes. Those are the ones that give us those overcast days with light rain or drizzle.
Okay, so we got cirrus cumulus-stratus and of course nimbus clouds, which bring the rain. But how does all that water actually get back down to Earth as precipitation?
Well, there are a couple of theories about this. One is called the collision coalescence theory. So you imagine all these tiny water droplets inside a cloudbird, they're bumping into each other, kind of like bumper cars.
Okay.
As they collide, they merge, they get bigger and heavier. And eventually they get too heavy to stay up there and they fall as rain.
So it's like a game of bumper cars in the sky that gives us rain.
That's one way to think about it. Another theory is the ice crystal theory. It's more common in colder clouds. And in these clouds, you have both ice crystals and supercooled water droplets. The ice crystals grow at the expense of the water droplets, eventually get heavy enough to fall, and then as they fall through warmer parts of the atmosphere, they melt and reach the ground as rain.
So depending on what's going on in the cloud, we get rain in different ways.
Right. And it's not always rain that falls from the sky.
Of course, you have drizzle and snow and hail.
Exactly. Drizzle's like a finer, gentler rain made of tiny water droplets. You have virga, which is rain that evaporates before it hits the ground, so you see these streaks hanging down from the cloud.
Oh, yeah, it looks like waterfalls coming out of the clouds.
Then there's sleet and hail. Those are the icy forms of precipitation. Sleet forms when rain falls through freezing air near the ground, and it turns into those little ice pellets. Hail forms inside thunderstorms.
Right.
Where strong updrafts carry water droplets high up into the freezing atmosphere, and as these hailstones get tossed up and down, they collect layers of ice, grow bigger and heavier.
Yeah, hailstorms can be pretty intense.
So,
And we also classify rainfall based on what causes the air to rise and cool and eventually form that rain.
right, so there's convectional rainfall. It happens when the sun heats the ground and the air above it. That warm, moist air rises, cools, and condenses and forms those big cumulonimbus clouds.
Like those summer thunderstorms that come out of nowhere.
Exactly. Those often bring sudden, intense downpours. Then you have orographic rainfall. This occurs when moist air is forced to rise over a mountain. So as the air climbs, it cools, condenses, and releases its moisture as rain on one side of the mountain.
So that's why one side of a mountain might be super lush and the other side is dry.
Exactly. That's the effect of orographic rainfall. And then there's cyclonic or frontal rainfall. This type happens when warm, moist air gets lifted over a mass of cold air.
So those clashes between warm and cold air masses lead to rain.
Right. It often happens at weather fronts, which are the boundaries between these contrasting air masses. Okay, so we've covered rainfall. Now let's shift gears a little bit and talk about wind. What makes the wind blow?
Yeah, I've always been curious about that. What makes the wind go?
Well, it all starts with atmospheric pressure. It's the weight of the air pressing down on a given area. This pressure is influenced by temperature and altitude.
Okay.
Warm air being less dense exerts less pressure. Cold air is denser, so it exerts more pressure. And as you go higher up in the atmosphere, there's less air above you, so the pressure decreases.
So basically air flows from high pressure to low pressure, trying to balance things out.
Exactly. The greater that pressure difference, the stronger the wind. But it's not just about those pressure gradients. The Earth's rotation also plays a big role, something called the Coriolis effect.
The Coriolis effect. Yeah, I've heard about that, but it's always a bit hard to picture.
Okay, so imagine you're standing on a spinning merry-go-round and you throw a ball straight ahead. To you, it looks like the ball's going in a straight line, right? But to someone watching from the ground, it looks like the ball is curving.
Okay, I could see that.
So the same principle applies to the Earth's rotation. Because the Earth is spinning, anything moving over its surface, including the air, is deflected from its path.
So it's like the Earth puts a spin on everything.
Exactly. In the northern hemisphere, this deflection is to the right, and in the southern hemisphere, it's to the left. This Coriolis effect has a huge impact on wind patterns.
So that's what creates those swirling patterns we see on weather maps.
Exactly. It's not just pressure differences, it's also the Earth spinning. And of course, friction also plays a role in how wind blows. Things like mountains, trees, and even buildings, they create friction that slows down the wind.
So that's why we usually have stronger winds out at sea.
Right. Fewer obstacles out there. Okay, so we have these pressure gradients, the Coriolis effect and friction. They all work together to create wind patterns. And to really understand global wind patterns, you need to look at those belts of high and low pressure around the planet. They're the driving force behind large-scale wind systems.
So those pressure belts, they're like the engines of the atmosphere.
You could say that. So one of those is the doldrums, or the intertropical convergence zone. It's a belt of low pressure near the equator.
The doldrums, that's where sailors used to get stuck, right?
Yeah, very light and variable winds there and a lot of rain.
Not the best place to be if you're trying to sail across the ocean. And what about the horse latitudes?
Those are belts of high pressure located around 30 degrees north and south of the equator. They have sinking air, clear skies, and very little rainfall. That's where many of the world's deserts are located.
So these pressure belts, they shape the entire planet in a way. It's pretty amazing.
They do. We also have subpolar lows, which are belts of low pressure at around 60 degrees north and south of the equator. and then the polar highs, which are areas of high pressure over the poles.
Okay, so we have this alternating pattern of high and low pressure.
Right, and that's what drives those large-scale wind systems like the trade winds. They blow from the subtropical highs towards the ITCZ.
Right, the trade winds were super important for those early explorers.
They relied on them to navigate. Then you have the westerlies. They blow from the subtropical highs towards those subpolar lows, and they bring warm, moist air to the west coasts of continents. And finally, the polar easterlies, they blow from the polar highs toward the subpolar lows, bringing those cold winds from the polar regions.
It's like the atmosphere is this giant conveyor belt moving heat and moisture all over the place.
That's a good way to put it. And then those large-scale wind patterns are further influenced by where the land masses are and where the oceans are.
Of course, right, because
Wow.
land and water heat up and cool down at different rates.
Exactly. So in the northern hemisphere where there's more land, the wind patterns tend to be more complex and variable. And what about jet streams? Have you heard of those?
Yeah, those are those fast-flowing air currents high up in the atmosphere.
Right. They're narrow bands of very strong winds that blow in the upper troposphere at pretty high altitudes. They typically blow from west to east, and they can reach some incredible speeds.
How fast are we talking?
Over 300 kilometers per hour.
Wow, that is fast.
They play a crucial role in influencing weather patterns. They steer storms, they influence temperature, and even cause sudden changes in wind direction.
So jet streams are like these powerful rivers of air high above us.
Yeah, that's a good analogy. Okay, so we've gone from condensation and precipitation to atmospheric pressure and wind systems and jet streams.
It's all connected, right? All these different parts of the atmosphere, they work together.
Exactly. It's like a giant puzzle. And in the next segment, we'll talk about air masses fronts, cyclones, thunderstorms, and even those beautiful auroras.
Sounds good. Can't wait to dive in. All right, so we're back and ready to keep exploring. In this last part of our deep dive, we're going to be talking about weather systems, all those things that make our weather so dynamic and exciting.
Exactly. Those are the forces that bring us rain, snowstorms, those clear sunny days. It's a whole system.
Okay, so where do we start?
Well, let's start with air masses. They're these large bodies of air that have pretty much the same temperature and humidity throughout. And they form over specific regions like a huge chunk of land or a big expansive ocean. And as they travel, they carry those weather conditions with them.
So it's like a giant air parcel that picks up the weather from where it was born and then brings it somewhere else.
That's a good way to think about it, yeah. So imagine an air mass forming over a warm tropical ocean. Well, it's going to be warm and moist, bringing humid, muggy weather wherever it goes. But an air mass that starts over a cold continent that's going to be cold and dry, bringing chilly, clear conditions.
So that's why we have such different weather in different parts of the world.
Exactly. And we classify air masses based on their temperature and moisture. We have maritime tropical air masses. Those are the warm, humid ones from the oceans. Continental tropical air masses form over those hot, dry deserts, so they bring scorching temperatures and really dry conditions.
Makes sense. And then what about the cooler air masses?
Well, there are maritime polar air masses. Those form over cold oceans, bringing cool, moist air. And then continental polar air masses. Those form over cold continents and bring those freezing temperatures and dry conditions.
So we got all these different air masses moving around, kind of like personalities of the atmosphere. But what happens when those different air masses run into each other?
Well, it's not always a peaceful meeting. It's more like a clash of titans. And those zones of interaction where they meet are called fronts.
Fronts, yeah.
Right.
We hear that all the time in weather reports. So what exactly is going on at a front?
Basically, it's a battleground between contrasting air masses. Depending on which air mass is moving in, you get different types of fronts. A cold front happens when a cold air mass pushes into a region where there's warmer air. Cold fronts often bring really dramatic weather changes with strong winds, heavy rain, sometimes even thunderstorms.
So those sudden drops in temperature, the gusty winds, those dark clouds, that's all a cold front moving in.
You got it. A warm front, on the other hand, is a little gentler. It's when a warm air mass slowly moves into an area where there's colder air. Warm fronts usually bring light to moderate precipitation over a wider area, so you get those prolonged periods of drizzle or steady rain.
Warm front.
Yeah.
Slow and steady cold front. Sudden and dramatic.
That's a good way to think about it. And then there are occluded fronts. Those form when a fast-moving cold front overtakes a warm front and lifts that warm air completely off the ground. Occluded fronts can bring a mix of weather conditions depending on what those air masses are like.
So occluded fronts are a bit more unpredictable.
Exactly, they can be. And then you have stationary fronts. That's when a front just stalls out. Neither air mass is really moving, so you can get long periods of cloudy, wet weather because those two air masses are just stuck there.
Okay, so fronts are basically where the action happens in the atmosphere.
That's a good way to put it. And these fronts, they play a big role in forming larger weather systems like cyclones.
Cyclones, those are the big storms we see swirling around on those weather maps.
They are. Cyclones are large, rotating weather systems with low pressure on the center. There are two main types, tropical cyclones and extratropical cyclones.
Let's start with tropical cyclones. Those are the ones we hear about during hurricane season.
Yes, exactly. Also known as hurricanes or typhoons, depending on where they form. And they form over warm ocean waters near the equator. They get their energy from the heat released when water vapor condenses. That creates those giant thunderstorms that spiral around a calm center, which is called the eye.
So the ocean kind of fuels those storms.
It does. And tropical cyclones, they're known for those intense winds, torrential rainfall, and something called storm surge, which is a rise in sea level caused by the storm's winds pushing water towards the shore.
Yeah, those storm surges can cause a lot of damage.
Definitely. Now, extratropical cyclones, those form outside of the tropics in the middle latitudes. They're often associated with those fronts and jet streams we were talking about, and they can bring a variety of weather conditions like rain, snow, winds, and even thunderstorms.
So extratropical cyclones are the ones that bring us those changeable weather patterns in those mid-latitude areas.
That's right. And both tropical and extratropical cyclones, they have rotating winds thanks to that Coriolis effect.
So in the northern hemisphere, they spin counterclockwise.
Yeah.
In the southern hemisphere, they spin clockwise.
Exactly. Okay, now let's talk about thunderstorms. Those localized weather systems that bring those flashes of lightning and those booming thunderclaps.
They're always both fascinating and a little bit scary.
Yeah, they definitely have a presence. They form when warm, moist air rises really rapidly, creating those cumulonimbus clouds. And inside those clouds, you get strong updrafts and downdrafts, and that creates turbulent conditions that drive the storm.
Right, and those updrafts are what keep those hailstones suspended in the clouds so they can get bigger and bigger.
That's right. Hail is one of the hazards associated with thunderstorms. You also have heavy rain, strong winds, lightning, and tornadoes.
Tornadoes. Those are amazing, but definitely terrifying.
They are. Tornadoes are rapidly rotating columns of air that stretch from a thunderstorm all the way down to the ground. You see those funnel-shaped clouds, and they have incredibly high wind speeds.
Yeah, those winds can cause a lot of destruction.
They can. Tornadoes are pretty small compared to cyclones, but they're very powerful.
Wow, okay, so we've covered a lot here. Air masses, fronts, cyclones, thunderstorms, tornadoes.
We have. Oh, and before we wrap up, we can't forget about those auroras. Remember we talked about the thermosphere? That's where those beautiful displays of light occur.
Oh yeah, the northern and southern lights, those shimmering curtains of light. What causes those?
Well, it's all about the interaction between the sun and the Earth's magnetic field. Charged particles from the sun called solar wind are constantly flowing towards the Earth.
Okay.
And when those particles collide with atoms in our atmosphere, those atoms get excited and they emit light.
So it's like a cosmic light show orchestrated by the sun and our planet's magnetic field.
Exactly. And the different colors you see in the auroras are due to different types of atoms getting excited. Green, the most common color, is produced by oxygen atoms.
That's amazing. It's like we're connected to space through those auroras.
I bet.
This has been a really incredible journey through climatology and atmospheric science. I've learned so much.
It's a fascinating field, and it's constantly evolving. We're always learning new things about how the atmosphere works and what influences our weather and climate. And that knowledge is really important, especially as we face challenges like climate change and extreme weather events.
Well said. It's been a fantastic deep dive, and I want to thank you for guiding us through it all.
It's been my pleasure.
And to everyone listening out there, thanks for joining us on this deep dive. Remember to like and subscribe, hit that notification bell so you don't miss out on future episodes. We'll see you next time.